Oh, I see we forgot to add a title for the discussion.
Yes. So the discussion was magnetic fields in accretion disks.
That's right. Yeah.
And now it's your turn, and we see the PowerPoint.
Okay. Okay. Great. So yeah. So Asaf and I are going to, for about half an hour, lead a discussion on magnetic fields. We've heard a lot this morning about different accretion models and different accretion geometries and lots of very nice simulations. A common theme running through all of that is, of course, the role of magnetic fields. So that's going to be the focus of our discussion. Asaf, do you want to just chat for a couple of minutes about these first couple of slides? Then we'll go into open questions.
Yeah. Okay. Sure. So yeah. So we just grabbed like a small collection of things to give the feeling. So the common wisdom that people are using is that magnetic field need to be an equipartition or close to equipartition. And what you see here on the left is one of the first numerical simulations that were done by Gumenchev et al. Nearly 20 years ago that shows that. And there is a good reason to think that we should have an equipartition, and the reason is, of course, because the magnetic field grows faster than the kinetic energy as we go down the radius on the one hand, but then on the other hand, it needs to dissipate its energy, or otherwise we won't get the inner accretion disk. So people, this is something which is very long been thought of, during the 70s, nearly 50 years ago, and it had been simulated in the last 20 years. And then to the right, what we're seeing is a simulation that we took from a paper by Sasha 10 years ago. And also Matthew had a very nice presentation about that, which essentially argued that in order to get efficient jet emission, as we're seeing in the low hardening quiescent states, we also need to have close to equipartition magnetic fields in order for the Blandford-Znayak process to take effect. So this is essentially sort of a common wisdom that many people would argue, but then when you look at the literature, you see that people actually just nearly take it for granted. If you can go to the next slide, there is a small promotion here. I think it's the next, another one. Yeah, this one. There's a small promotion of a talk by John Wallace will be given on Wednesday, where we actually try to check this assumption on real data. There are two objects here in the quiescent state. And what we find out that in 3 cases that have been checked, the actual values that one gets when you feed the data, in the millimeter wave bands, there were not so much data available until a few years ago about that. It's actually far less than equipartition. So there seems to be some sort of a controversy here. So it's a small promotion for John's talk on Wednesday morning, so wait for that. Right, so given this discrepancy, now I'll let Chris go on to the next slide, which is, here we go.
Yeah, so sort of, I think this is a few questions that we've come up with just to help sort of get the discussion going. And just sort of quickly walk through what's in our minds when we wrote this down. I mean, the first topic here, what determines large-scale fields threading the inner disk? I mean, I think it's fair to say that of all the beautiful simulations that exist in this field, it is still true that the final outcome of the simulated accretion disk is largely shaped by the initial conditions of the magnetic field, in the sense that if there's a significant colloidal flux in the initial conditions, that will lead to final accretion disk setups with very strong flux in. So how does nature do this? What determines the large scale magnetic field configuration in real accretion disks? Is it all advection from the actual source of accreting material, in which case there's a very interesting environmental dependence of the final state of the inner accretion disk, or is there a dynamo action at work in the disk, or is it something else we haven't thought of? So the second point for discussion is, and we don't have to go through these in order, I think this is just to seed people's thoughts. What is the role of MHD turbulence in destroying the field, transporting the field, advecting the field, growing the field through MRI and through turbulent action? And are we actually capturing the necessary ingredients of the disk turbulence well And I mean, just to throw one thing out, for example, is do we have the correct dependence on Prandtl number, for example, which is something that's been discussed a lot. One point which I think Saf and I agreed was particularly important sort of theoretical point for anchoring some of the, or for some of the controversy that exists in this field is, can a geometrically thin sort of cool disk of the kinds that we think could generate, you know, very strongly broadened ion lines, can that actually support the large scale fields we need to drive Blanford-Znaiec jets? So, and if not, then what does drive the jets in luminous hard states, or equivalently, or alternatively, what gives you the reflection in luminous hard states? And then to sort of pick up I know there was a question earlier on that Victoria asked to defer to the discussion. You know, is the lamppost real? And if so, if it is, what's its physical nature? And just to sort of again say something hopefully is obvious, just because we don't see it in MHD simulations doesn't mean it's not there. So let's throw it open for discussion. Try my best to juggle the different forums here. Somebody in the room will have to look out for us because we can't see the room.
So, okay, so for the moment, actually, I have one question. So there's no questions in the room yet. Yeah.
Can you identify yourself, by the way?
Yeah. I'm Pier-Olivier Petrucci. So yeah, your open questions are very interesting actually, and I think that most of the simulations now, recent simulation, seems to show the advection of magnetic field. My question is that the next step to answer to most of these questions could be the inclusion of radiations in the. I mean, there are already simulations with radiations, but I'm talking about, for example, the difference between Blanford-Znaiec or Blanford-Payne type of simulations or type of jets. Do we expect bright Blanford-Znaiec jets compared to Blanford and Page jets? What will be the limitation? What are the limitations in the simulation yet to discriminate between these two jet processes in terms of radiations? It could explain actually some of the questions that we have. So, but I'm asking to the expert of simulations. Yeah, actually, I have no answer.
Good question. Do we have any of the Matthew or?
Yeah, I'm here. I mean, what we know from like non-radiative simulations is simply that let's say the power that you can get and the amount of collimation that you can get in a Blanford and Payne, like outflow, I prefer to call it outflow instead of a jet, is just inconsistent with what we see, for example, in AG and M87, where these flows really reach relativistic velocities of, you know, gamma at least and few, which is simply not attainable in an ideal scenario. But when we add radiation, we simply do not know exactly what the speed of the outflow could be. But my feeling would be that still, even if the speed is higher, it would be hard to really collimate an radiation like pressure driven outflow in something which would be consistent with a jet, for example, like M87 or any XRB.
I think if I can add some comment from a different perspective, I think you can think of it in terms of energetics. You should know how much energy you may have in in the radiative field, which is as much as you can have in the thermal radiation or in the electrons, assuming that they are fast cooling, and that's it. You don't have more energy than that in the radiative field. So if the energy density in the magnetic field is larger, then radiation cannot be that crucial. On the other hand, it could be quite important. So I guess I would look at it from this perspective.
Poshak, you have your hand up. Do you want to chime in with something?
Hello.
Hello.
Can you hear me?
Yes,
Hi.
I can hear you.
Excellent. Thanks for the wonderful event. I'm sorry I can't be there, but it's nice and sunny here in the UK today, at least.
Which UK are you in?
Clearly not Cambridge.
Yeah.
So parallels are often drawn with the solar corona when we come to talk about magnetic fields. So I'd really like to understand. I've heard, contradictory claims as to how much we can really infer from understanding and comparing with the sun. What are people's thoughts in this regard with regard to the result Asaf just presented, the Wallace and Peer result? Would those sorts of magnetization levels also be seen in solar flares, for example, or is that just a completely different regime?
Anybody particular want to address that, or I can try to chime in on that? Any experts on solar corona?
No one in the room, apparently.
No one in the room?
We need to give, next time you organize a meeting like that, we may want to invite somebody who does solar physics.
Yes, I mean, Poshak's point is very well taken, I think, and so it's an interesting question. If we took our very same codes, could we simulate, the sun? So always a question worth asking. And I'm not quite sure that we would like the answer we get. The solar corona, for example, all those beautiful flux tubes you see bubbling out of the sun and exploding out of the sun. I mean, there's almost certainly helicity is an important quantity there. The way that the flux tubes are wrapped up as they come out, and our code's not particularly good at conserving helicity, for example. They're also quite, the magnetic reconnections is very important. Of course, that's a classic topic to try to understand, and our understanding is incomplete there. So it's always interesting to try to anchor ourselves to that kind of work. Of course, the regime is extremely different. I mean, the energy scales are extremely different. The corona in the black hole accretion disk may well be very, very energetically important to the disk, whereas the corona to the sun is not particularly energetically important. So we shouldn't necessarily take the analogy too seriously.
We have a comment in the room.
Yeah.
Yeah, concerning that's a very good question. The question of, so do you hear me? Does it work?
Yes, we can hear you well.
Okay, Ilek here. And so, yeah, the analogy with the solar corona, I feel the most important component is that you mentioned the magnetic reconnection. There are different numerical tracks to try to model this. So first in GRMHD simulations by Bart Ripperda, for instance, they manage to parameterize the magnetic diffusivity and to really have an idea of what's going on at the microscopic scale. But for the microphysics, an alternative is particle in cell. And I present later this week particle in cell simulations to try to identify where magnetic dissipation occur and what's the impact in terms of particle acceleration. So that can happen also not only in the disk itself, but also in the corona, in the more tenuous, highly magnetized environment above the disk. And then, yeah, like in these situations, you can get a significant dissipation of electromagnetic energy given to the particles, and then non-thermal emission based on this. So that could be a possible track for explaining the coronal heating, but the coronal heating of black holes, not of the sun this time.
Yeah, thanks. And maybe can I just ask a question based on that? So is it true to say, or is it fair to say that the kind of processes you just discussed there is actually a breakdown of MHD? So it'll be a hard thing to capture in a pure MHD code. If we're trying to ask the question of whether how we can understand the lamppost, does that have to be potentially done outside of an MHD context?
There is a comment in the room.
So just to make an empirical comment on the analogy with the solar corona, we think of the jets and the microquasars as a radio event. But in fact, the radio luminosity compared to X-ray luminosity, for example, is very weak in these microquasars compared to the solar corona flares. So I tend to agree with Chris that the analogy is going to be difficult to understand the microphysics in a sense of reconnection could be similar.
Yeah.
But the radio emission is much brighter in the sun with respect to the other bands compared to.
I suspect
Just a second, could the speaker before just quickly state their name, because it's really hard.
Yeah, sorry, Ehud Behar, I'm sorry.
Okay.
Thank you, Ehud.
No, a good point, Ehud. And I think this is where we're certainly, when we're drawing any comparison with the sun, we have to differentiate understanding some of the basic physical processes, the MHD turbulence and reconnection, and anything associated with the actual radiative signatures. I think the radiation processes that are involved in the solar corona are going to be entirely different to those that are at play in black hole corona, or at least very different. The regimes are very different, so we can't take any comparison with the observables too seriously.
I would imagine that the magnetic quantum number is very different, no?
Yeah.
Okay, Dr. Phil?
Yes. So so I'm wondering, I mean, with all these kind of this confrontation of observations also with the data, right, which we have some clear examples, like obviously from M87 with the EHT data, but also now, I mean, recently with variability studies, right, we're getting more sophisticated at trying to model the signals that we see, like time lags and things. And there's a general pattern, for example, I think that most models of the time lags that involve fluctuations propagating through the flow require flows to be pretty fast. And yet observationally, we see that the disk is actually varying, or at least a black body emitting component or something looks like that, and contributing to those lags. So, you know, there's already sort of pointers. And the other aspect of QPOs, which Greg touched on in the previous talk, is that there's something else that may be needed, for example. And I think that there's a good point there, that we know that the field must affect the dynamics, right? Because jets are formed, right? So it's presumably could have a strong effect on QPOs and those sorts of quasi-coherent signals that we see. So what I wonder is, how far away are we from getting the data, getting the simulations, right? Because we're only, what, 10 seconds, Matthew mentioned, right, of the life. And is that enough to be able to capture a lot of this behavior and try and get a match and maybe use the timing data to actually constrain the magnetic field configuration? Is that something we're close to, or still very far away from?
Before you answer, just one general remark. Yes, everybody can contribute, but please raise your hand when you're on Zoom, because otherwise we don't know that you want to contribute.
Matthew, you want to respond to that? Or anybody? No, maybe not.
No, nobody in the room.
Hi, can anybody hear me?
We can hear you. Yes, yes. Can you identify yourself and then?
Yeah. Can you hear me? Can you see me?
You're very faint right now. When you first spoke up, you were.
Am I audible? Is it okay?
It's okay. Yeah, but maybe speak up. Yeah.
Okay, so I work some. I have done some work regarding solar corona and the launching of jets, the episodic jets as well, in my first project. So what we have done is we have taken the analogy of the ejection of coronal mass ejection from the sun, and we applied it to the for launching of blobby jets, the blobs. So what we consider blobs as these current carrying flux ropes, and we don't consider the magnetic reconnection, but we consider another model called toroidal instability model, wherein there's an instability called. So can you see this? If you can.
We can, but just to this is sort of an opportunity for open discussion, so we don't want to if you have a discussion point to raise.
Okay, so what we did is, so we applied the toroidal instability model, and we tried to explain the observations of the galaxy 3C120, the blobs in 3C120. And basically the high time profiles of the blobs, And so my question here is, so in the GRMED simulations, do we so do you get this flux tubes as do the magnetic fields evolve in your simulations to get these flux tubes, this kind of flux tubes?
That's a good question. So is there a tendency, you're asking, is there a tendency?
Yeah, because of the differential rotation of this of the disk. So we believe that this field line get twisted and forms the
is there a concentration into well-defined flux tubes? Yes, yes. So any of the folks who do the GRMHD simulations, do you have any thoughts on that? Whether Oliver, I think I saw your actual hand go up. Yeah. So
there is one other comment in the room.
Yeah, that's more like a follow-up question related to Shender, so also to MHD people, because in the first slide you showed, Chris, you do see, that's still Ilek speaking, by the way. You do see in the first slide in Sasha Tchaikovskoy and Matthew Liska's simulations, you really see a configuration where you start from colloidal loops in the disk, and the question is, could you actually get at some point these loops closing within the event horizon, within the ergosphere because of the accretion? And if so, is it susceptible to lead to configurations where you have the magnetic topology suitable for this type of coronal mass ejection?
Oliver, you have your hand up. I don't think we can hear you. Can you, Oliver?
There.
You're not muted, but we can't hear you.
Yeah, is your microphone not plugged in, or you don't have the right microphone settings?
I can add in the meantime another question which is related to that. I mean, the simulation that we saw were all ideal MHD. Now, it's not clear to me, you know, how good an approximation it is. I mean, it's obviously a quite good approximation, but it could be that, you know, life is not exactly ideal. So we might end up with some extra effect when we end up you know, viscosity there.
I mean, I think, you know, to expand on something that Matthew said, of course, it's really difficult to do convergence studies. It's very, very difficult to, almost impossible to prove you're converged. But I don't think that should stop you from being worried about these kind of things. Because I mean, there's a whole community of people who study turbulence, you know, pure turbulence, and their standard system is a periodic box. And they're still learning things about turbulence from that, from those, about MHD turbulence from those systems. So we must always be worried about these things. And as Saf says, you know, especially if you start to put non-ideal effects in. Oliver, are you ready yet, or are there other?
Actually, I have one question about the lamppost. So I'm Pier Petrucci. So concerning the lamppost geometry, so we have seen this morning that it was suggested by Martokia and Matt in '96, and the idea could be that that they, for any reason, that there may be a jet that collapse and produce hot sources of X-rays above the black hole due to any reason that prevent the production of large-scale jets. So this type of aborted jets can be an explanation in some conditions to the production of this lamppost type of corona. I would like to, yes, to ask two people doing simulations if they have catch this type of possible evolution of the jet.
Any thoughts on that?
Hey.
Matthew.
Yeah, hi. I'm back. Yeah, in these aborted jets in GRMHD simulations essentially don't happen, from what I've seen, on really the distance scales. The that would be necessary for a lamppost corona. We either have no jet, for example, in simulations with toroidal magnetic fields for thin disks, or we have like very weak jets, but usually these weak jets at least propagate for a few hundred RG before they are like killed by kink instabilities and other effects that arise from the interaction between the ambient medium and these jets. Plus also these very weak jets, the energy density in them is very low. So I'm not really sure that even if they would emit radiation, the radiation would be significant at all. Yeah, that's my feeling, that's my take on it.
No, thanks. Okay, I have just a few minutes left.
Oliver back or not yet?
No.
We have another comment. Right.
Ilek here. So Oliver cannot. We can hear Oliver, unfortunately, but his simulation with Bart Riperda and Fabio Bacchini are resistive GRMHD simulations now. And so they managed to go to Lundquist number high enough that the magnetic reconnection rate converge. So they still don't have, of course, like that's GRMHD, so you don't have the information on the particles themselves. But in terms of energy dissipation, they managed to reach like a regime thanks to adaptive mesh refinement, very high resolution, where they can actually really witness the formation of the plasmoids at the expected physical rate.
Okay, nice.
Yeah, now, do you hear me now?
Yes, we hear you well. Yeah.
Okay, I
Welcome.
lost a bit of the discussion, so maybe that was mentioned before, but yeah, on the topic of the plasmoids, indeed. So the hope here is, of course, once you start resolving these plasmoids, and also this is something that Matthew Liska and Bart did together in the harm code in 3D GRMHD. So the hope is that once you start resolving these structures, that the dissipation rate is totally governed by the plasmoid instability. So you might not actually be short on microphysics because it's actually, yeah, you actually already resolved the fundamental instabilities that take care of magnetic reconnection in this regime. So that's really quite exciting development.
Yeah, that's also, I would say, like really good that if it's indeed the case, like our simulations have shown that really close to the black hole, we're really dealing with something which is highly magnetized, that indeed the dissipation would really mostly happen in current sheets. And when you get in this plasmoid dominated regime, then hopefully that you are just converged in many ways.
Okay, so I think we're at time. Thanks.
Yeah.
Thanks for the discussion. I don't know if Asaf, you have any final
Well, thanks everybody for participating.
Thanks everyone. I think that was a good
So
discussion. Hand over to you, Victoria.
yeah, thank you from me. So thank all the speakers of this session. Thank you, Chris and Asaf. I know this is complicated, holding so many things at once, but it worked much better than I expected. Thanks, everyone. So we are coming back in the afternoon so that our colleagues from the US have a better chance to join. So we are starting at 4 p.m. European time, again, with a session that's more focused on observations, but not only, and a discussion on something that has been mentioned already today, namely disk truncation and just disk corona interaction. In the meantime, especially the speakers, take another look at Slack. Some of you have already answered questions. There are several more questions and quite a bit of a discussion ongoing. People who are in presence, enjoy the sun, don't get sunburned, enjoy the amazing Italian food, and while everybody else, enjoy your food at home, and see you later then.
Thank you very much, Victoria. Just a quick announcement. You can let your things inside the room if you want, because I will close the door. And I will reopen it at 3:30. So you can let everything inside if you want, it will be safe here.